What's new? Oh, there's new features. Okay. I'll look at them later. Okay. 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 So today we're going to go through mixed degree systems. So let's go ahead and jump in. So before we go into mixed degree systems, I want to go over some equations. The first one's going to be the parabola equation. Whenever we have a parabola, we use this standard form equation, which is y equals ax squared plus bx plus c. We've seen this one before, and we know a little bit about the relationships between these different variables. So if a is positive, we know that parabola opens upward. If a is negative, we know that parabola opens downward, and then we know how to identify the vertex, which is that x equals negative b divided by 2a, right? That would give us our vertex, which basically just represents this point right here. So that would represent our vertex, okay? We haven't gone over circles so much, but this is the circle equation, and we're not necessarily going to work with it today. I just want you to know the circle equation, because what we're going to be able to do is understand whenever we see graphs, how can we identify the solution points? So for a circle, the equation is x squared plus y squared equals r squared. And this is when you have the center of your circle at 0, 0. So basically the center part is located right there directly at the origin. And then your r will represent your radius. So basically how far or what your radius is from the outside to the middle point. So that's what r would represent in this instance. But again, I'm not 100% concerned with you being able to differentiate the circle equation. Just know that that is the circle equation. So when you see an equation like that, whenever you're graphing, you're going to get something that looks like your circle. But you'll see that in the graph. Okay. What we're really going to be looking at today is we're going to be able to graph a system of solutions and find their points of intersections. If they intersect at one point, then that point is the solution to the system because it makes both equations true, right? We know that to be true. Whenever you graph solutions and they have a point of intersection, that's going to give us a solution, and that solution indicates what makes both of those equations true. So we've been working with that throughout Unit 4, and so we're just going to look at what this looks as far as graphs.
Everything's okay with you, or you need somebody easier, right? They're all yours?
Mm-hmm.
Thank you.
Mm-hmm. Okay. So now we're going to look at what this looks like on the graphs. So here we have an example of lines and parabolas, and here we have an example of lines and circles. And so basically what you can identify is that the points of intersection are going to be your solution points, right? And we've gone over this before. So a line and a parabola. A system of equations with a line and a parabola can have 2 points, 1 point, or 0 points of intersection. And so it's just showing us examples of that.
Good morning, Greenhouse. Can you please stand for the Pledge of Allegiance? I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible with liberty and justice for all. And now the Texas flag. Honored by Texas flag, I pledge allegiance to thee, Texas, one state under God, one and indivisible. Please remain standing for a moment of silence. Thank you. Have a great day.
Okay. So basically what we can look at on these graphs is we can identify the solution points, which are basically going to be the points of intersection. So if we look at this first line, and I'll go ahead and color coordinate it, this line right here, what we notice is that line and that parabola have 2 solutions, 2 points of intersection, one right here and one right here. So we would say that that has 2 solutions, right? Because there's 2 points of intersection with the parabola. Here's another line that we have. this blue line. And what we notice is it only has one intersection. So that would mean it has one solution. And here we have another line. And you can see that it never intersects with that parabola. So that would mean it has no solutions. So basically what we should be able to identify here is that if you have a point of intersection, those are going to represent your solutions for that system of equations. Basically, it's going to make both of those systems or both of those equations true. Okay, here's an example of a line and a circle. It says a system of equations with a line and a circle can also have 2 points, 1 point, or 0 points of intersection. So we can look at these. This line right here, it has 1 point of intersection, right? It intersects that circle 1 time. So we would say that has one solution. Here's our other line. We'll notice it has 2 points of intersection. It intersects that circle twice. And so that would represent 2 solutions. And then here would be another line. It's not marked here, but if we had one line that existed right here, through here, we notice that there's no points of intersection as far as it goes to the circle, right? It may intersect those other 2 lines we're looking at in real circle. And what we notice is there's no points of intersection. It doesn't intersect that circle. So we would say that this has no solutions or 0 solutions. Okay. So basically the takeaway here is that whenever you have 2 systems of equations graphed or multiple systems of equations graphed, what you're trying to identify is that point of intersection. That point of intersection is going to give you your solutions, thereby making both of your equations true. Okay, does that make sense? Does anyone have any questions? So here it says solve this system. So basically we're given a system of equations. You can do this algebraically or you can graph it. If you were to graph it, I can go ahead and show you what that would look like. You can still graph it to find your points of intersection. So let me share this with you. I'm just going to do my window because I'm not 100% sure which one. Okay, so here is me graphing both of those expressions. The first one said h is equal to 144. The other one said h is equal to 96t minus 16t squared. Okay, our point of intersection is going to be where those 2 intersect. And because the first one says h is at 44, my first system or my first equation would just be graphed right here. And so this point where those 2 intersect, where my parabola intersects and where that point intersect, is going to be my solution to this equation. Therefore, my solution to this equation is 3 and 144. That would be my point, which would make both of these equations true. Okay, so I can easily just represent my solution point by graphing it. Or I can do it algebraically, and I can show you how to do that very briefly. If you do choose to do it algebraically, you'll realize that you get the same solution. Okay. So whenever I'm doing this algebraically, again, it's up to you whether you want to do it graphically or algebraically. If I were to do this algebraically, what I would basically do is substitute h into the second equation, right? So the second equation has h right there, so I want to substitute h into that equation. So 144 is equal to 96t minus 16t. And what I want to do is I want to set that equation equal to 0. Setting it equal to 0 will give me a parabola equation, which will make it easier for me to factor and find the solution to this set. So setting this equal to 0 would basically, the easiest way to go ahead and do it for this particular problem is to take this part of the equation and move it over. And again, you can do it by doing it like this, or you can do it by graphing it. And basically, this equation is the same thing as that equation, but it's just equal to 0. So So that is making it equal to 0. Basically, I have it in my standard parabola form, but now it's equal to 0. And so now what I can easily do with this is I can factor. We've worked with factoring in the past. Easiest way to factor this one is to divide by 16 on all of these. Oops, I just realized that I forgot that 6. It is 96. 96, okay. So I'm dividing by 16. That allows me to take out that 16, and now I'm left with t squared and minus 6t. Plus 9. Right, so I basically just taken 16 out of all of those different components to allow me to factor. Now I can factor that inner part, that t squared minus 6t plus 9. And when I factor that, I get t minus 3 and t minus 3, which is equal to 0. Okay, so basically I've just factored my original equation. And what this tells me is that one of my points of intersection is at, well, t minus 3 equals 0, plus 3 on both sides. My point of intersection is going to be at t is at equal to 3. So basically my x value is going to be t is equal to 3, which I identified when I graphed it, right? So again, it's up to you whether you want to graph it or you want to do it algebraically. But I need the other part of it. So yes, I know t is equal to 3. And so how do I get my h? Well, luckily for you in this equation, it says h is equal to 144. And so h would represent your y. And so here your y would be equal. Y is equal to 144. And so therefore your point of intersection is going to be at 3 and 144. Okay. In my opinion, the easiest way to go ahead and solve this is to actually go ahead and graph it, because you do have that function to graph it on the equation, on the calculators that you have whenever you take exams. So that's going to be the easiest one to do. But if you want to do algebraically, this is how you do it. Okay, questions? So the 0.3 and 144 is going to be the solution to the system of equations. It's going to make both of those equations true. Okay. Here is the next set. It says solve the system. So you could also do this graphically, algebraically if you wanted to, or you could do it graphically. I will show you how to do it graphically because in my opinion, that's the easiest thing to do. So I want to say, it's going to be this one. Nope, that's not it. I graphed them both in advance just to be sure. So now I think it's this one. Okay, so here's me graphing that. X plus y equals 8, y equals 2x squared plus 5. And so your points of intersection, you have that parabola, and one is a line, so you have a parabola and a line. The points of intersection will be those points where those two intersect. So the first one would be at negative 1.5 and 9.5, and the other one would be at 1 and 7. Okay. So that is true for both of them. And so that would be your points of intersection. That would be your solution. Okay, but again, you can do this algebraically if you wanted to. I'll just quickly show you what it does look like if you were to do it algebraically. Give me 1 second. So if you were to do this algebraically, you would basically follow each of the steps. You want to substitute 2x plus 5 for y into the first equation and set it equal to 0. And so basically you're just factoring. When you factor, then you're going to plug it in, and then you'll get those two intersection points. So that's if you wanted to do algebraically. But if you did want to do it graphically, you can also do it that way. Okay. And if you wanted to access this to see how to do it algebraically, it is available for you under the classwork tab under Wednesday and then 4.5. Okay. But for the purpose of this class, it's easier to do it graphically. Okay. Questions? Okay. Okay, let me go back to sharing. And we are almost done. Just each of the steps. Okay, so basically what we should be able to do today is to be able to identify how many solutions does a graph show you. And so here's an example. Whenever you have two parabolas, this first diagram would show you 0 solutions because there's no points of intersection. This second diagram would show you 1 solution because there's 1 point of intersection. This one would show you 2 solutions because there's 2 points of intersection. This one would also show you 2 solutions, right, because there's 2 points. And then this one, what you should be able to identify here is that they're kind of overlapping each other. I know it's not a good diagram of it, but that's what it's saying. They're basically overlapping each other. And so that would mean there's an infinite many solutions, right? And so whenever you see two parabolas being graphed, what you want to identify is that point of intersection, because that point of intersection is going to tell you how many solutions you have. And just a reminder that those solutions indicate what's going to make both of those equations true. Okay. What if you have a parabola and a circle? Well, again, you're just looking for those points of intersection. Here you notice there's no points of intersection, so that would be 0. Here you notice there's 1 point of intersection, so that would be 1. Here there is 2 points of intersection, so that would be 2. Here there are 3 points of intersection, so that would be 3. And here there are 1, 2, 3, 4 points of intersection, so there would be 4. So you just want to identify how many points of intersection you have, and that will tell you how many solutions you have. And then lastly, whenever we have 2 circles, we can again have 0, 1, 2, or infinite many solutions. This first one's going to be 0. This is 2 diagrams of 0. This is your first diagram, which again has 0 solutions because they don't intersect anywhere. This one, they don't intersect anywhere either. Here they intersect at this 1 point, and so that would be 1 solution. Here they intersect at 2 points, and so that would be 2 solutions. And here again, it's not the best diagram, but it's basically just showing these 2 circles overlapping each other. And so we would say that that has infinite many solutions. Okay, but basically you're just looking for those points of intersection. Okay. Lastly, what I want to go ahead and do is here is an example of where you have a circle equation and a parabola equation. And you can solve this algebraically, or what you can go ahead and do is graph it. So I'm going to show you what it looks like if you graph it and identify those points of intersection. This is your example. This is me graphing both of those, and you're just looking for those points of intersection. So where does that parabola and the circles intersect? And so it does so here, it does so right here, it does so right here, and right here. And so those are all points of intersection. You do see other points indicated here, but what you realize is they do not intersect at those points, and so we want to use those. We only want to identify where there's a point of intersection, where is there an overlap. And so this one you would have 4 points of intersection, and you can identify them like that. Okay. Or you can do it algebraically if that is your preference. And like I stated before, you do have a resource available to you which can tell you how to do it algebraically if that is your preference. And so you would just go to classwork tab, go to here, and it's going to be this last one. And so this would show you how to do it algebraically if that was your preference to do so. Okay, questions? Okay.
No, ma'am.
So just a review, solution methods for mixed degree systems are the same as those of linear systems. So if you want to go ahead and find those solutions, you can either graph it, or you can use elimination or substitution to basically do it algebraically. Either way, you'd be able to identify your solution points. It's up to you what type of method you want to use to solve them. A graphical solution can be a line of parabola that opens upward or downward, or a circle with its center at the origin. So we can graph all these different types of expressions and find solution points for them. For distinct linear quadratic systems, 0 to 2 solutions are possible. For distinct quadratic systems, 0 to 4 solutions are possible. And for non-distinct systems, there's an infinite many solutions. So basically, we identified how many different types of solutions we can get. And so that's what it is reviewing. So here are the different problem types that you may encounter. You may be asked to solve the systems of equation by graphing, which we're able to do today, which basically looking for is that point of intersection. That point of intersection will tell you what expression can make both of those systems true, therefore being your solution set. And then if you're going to do it algebraically, you can solve systems by using elimination, and this is the steps you would do to do elimination, or you can solve it by doing substitution, and that's the steps to do it by substitution. Again, the easiest way is to do it graphingly, but it is up to you what your preference is as far as finding those solution points. Questions? So what we're able to do today is we're basically able to see if I were to graph these different equations, how would I identify my solutions? And the key word is you're trying to identify your points of intersection. Your points of intersection are going to represent the values which would make both of your equations true. Yes. Okay. So that's basically the gist of today. Like I said, it's not very lengthy. But if there's no other questions, you guys may log off, and I will see you guys tomorrow. Bye, guys.
Bye, Miss.